Hello everyone, my name's Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams, and this video is going to focus on some organic chemistry past paper exam questions. So these questions are designed for A2 students and they're taken from the WJEC exam board. They would still be just as applicable for other exam boards as well, but these are taken from the WJEC Unit 4 past papers, which is all about organic chemistry. If you find it helpful, please remember to like, subscribe, and keep checking back for more content. My advice would be, if you've not had a go at these questions yet, the question will appear on the screen. Maybe pause the video, have a go at the question yourself on a bit of scrap paper, and then unpause and watch me go through it. And hopefully then you can reflect on things that you know, things that you don't know, things that you still need to revise. So the first question here has this rather random looking molecule called TATP, and you're shown the skeletal formula of it, and you are asked to give the molecular formula for the compound. So the molecular formula is counting all of the atoms. So I'm going to get a little highlighter pen to try and help with this one. Each of the points on a zigzag counts as a carbon. So you've got 1, 2, 3 carbons there, and then another 3 carbons there, and then another 3 carbons there. So that gives you 9 carbons in total. And if I just change the highlighter now to green, you've got 1, 2, 3, 4, 5, 6 oxygens. So it's going to be O6. And then lastly, we need to count the number of hydrogens that are present. Well, with skeletal formula, you don't see the hydrogens, but let's just zoom in on one of these little groups here. So this bit that I've highlighted yellow is a carbon, and it's making 4 bonds, so it can't be bonded to any other hydrogens. However, these 2 carbons here are making 1 bond to the other carbon, which means they're free to bond to 3 hydrogens. So there are 6 hydrogens in total here, and then another 6 here, and then another 6 here. So that would give you H18. And therefore the answer would be C9H18O6. Don't try and simplify that to give the ratio. That's called the empirical formula, and that's not what the question is asked for. If it did ask for that, you could divide each of these by 3 if it did ask for the empirical formula. So you would end up with C3H6O2. But that's not what the question is asked for. Okay, so this next question is about decarboxylation using soda lime. Now, when you heat something with soda lime, you kick out the carboxylic acid group, and you end up with the alkane that is 1 carbon shorter than what you started with. So to make propane, you must have started with a molecule that had 1 extra carbon, so it would be butanoic acid. And when you decarboxylate butanoic acid, you lose the carboxylic acid group and you end up with propane, which is 1 carbon atom shorter. Right, you then have a question here where you've got 3 different compounds that you have to rank in order of increasing acidity. So let's go through them. The easiest one to start with, I suppose, is the amine shown here, labelled B. Now an amine has a lone pair of electrons on the nitrogen, which actually makes it a base. So in terms of being acidic, it would be the least acidic because it's actually a base. So B would be the least acidic. And then you've got A and C. Now A has a carboxylic acid group and a phenol group, whereas B only has the phenol group. And the carboxylic acid is more acidic than the phenol, so therefore C would be the next most acidic. Phenol is ever so slightly acidic, but not so much, whereas a carboxylic acid group is even more acidic again. So the carboxylic acid would be more acidic than the phenol, and that's due to the stability of the carboxylate ion that forms. On the next question here, you've got two compounds, pentan-2-one and one phenyl butanone. And you have to suggest a simple chemical test that will distinguish between the two molecules. Now, they both contain ketone groups. However, if we look here, or the one on the left, the ketone group is next to a CH3. This is called a methyl ketone. Whereas one phenyl butanone, the C double bond O, is not next to a CH3, it's next to a CH2. And the reagent that you use to identify a methyl ketone is sodium hydroxide, NaOH, and iodine. And effectively what happens is the hydrogens of the CH3 substitute for iodines, and you end up kicking out CHI3. And what that means is that pentan-2-one would give a yellow precipitate, yellow PPT, precipitate of the CHI3, which is produced, and then you would get no observable reaction for one phenyl butanone. So if you want to test for a methyl ketone, you use sodium hydroxide and iodine, and it will give a yellow precipitate. This test can also be used to distinguish for secondary alcohols that can be oxidized to methyl ketones as well. So something like butan-2-ol would also give a yellow precipitate when treated with sodium hydroxide and iodine. The next question is more of a calculation than organic chemistry, but here you've got aminoethanoic acid reacting with nitric acid to produce nitrogen gas, and it says calculate the maximum volume of nitrogen gas produced at 100 degrees Celsius and 98 kilopascals when 0.3 moles of aminoethanoic acid reacts in this way. Give your answer in decimeters cubed. Okay, so the equation that we're going to need to use is the ideal gas equation, P times V equals nRT. Now it tells you that there are 0.3 moles of aminoethanoic acid, which is this one here, which means that the moles of the nitrogen must also be 0.3 moles because they're in a 1-to-1 ratio. And the aim is to calculate the volume. So the first thing I'm going to do is rearrange this equation. So I'm going to say that V equals N times R times T over P. And at this stage, we need to plug some numbers in. N is the number of moles, so that's the 0.3. R is the gas constant, which is 8.31. T is the temperature, which is 100 degrees Celsius, but we have to convert that into Kelvin by adding 273 to it. So that would become 373 Kelvin. And the pressure is 98 kilopascals. Now that needs to be in pascals, so it'd be 98 times 10 to the power of 3 pascals, or 98,000 pascals. I've just times it by 1,000 there. Now when you put that into your calculator, it comes out as 9.49 times 10 to the minus 3. And when you put everything into the ideal gas equation with the correct units, it comes out in meters cubed. So we need to times that by 1,000 to put it into decimeters cubed, which is 9.49 dm cubed. Right, the next question says hydroxyethanoic acid can also be prepared by reacting chloroethanoic acid with aqueous sodium hydroxide. Explain why the reaction mixture needs to be acidified to produce hydroxyethanoic acid. So effectively what's happening here is you're taking the chlorine on the chloroethanoic acid. If we were to draw this out, chloroethanoic acid would look like this. And you're refluxing it with sodium hydroxide, which is effectively OH minus. And what's happening is the OH minus is substituting for the chlorine. To give an alcohol. However, because you're using sodium hydroxide, which is Na plus here as well, what happens then is rather than forming the carboxylic acid that you started with, you end up forming the salt, the sodium salt of the carboxylic acid. And this is why this needs to be acidified with H+, and that'll give you the hydroxyethanoic acid, which is 2 carbons here, double bond to O to OH, and then the OH, and then your hydrogens. So it needs to be acidified because under the alkaline conditions that the reaction took place in, you'd form the salt of the carboxylic acid. The next question is a mole calculation, and you've got ethanoic acid reacting with chlorine to form chloroethanoic acid. And it says calculate the increase in mass that occurs if chloroethanoic acid is the only organic product, assuming that you start with 89 grams of ethanoic acid. So the way I would tackle this problem is I'd say 89 is the mass, divide it by the molecular mass, which is 60, times it by the new molecular mass, which is 94.5, and that'll give us the maximum amount of mass of the chloroethanoic acid, which is 140.18 grams. But it says calculate the mass increase. So you do 140.18 minus the 89 that you started with. And that gives me 51.2 grams to 3 significant figures. So the mass has gone up by that amount. Right, the next question is about percentage yield. So it says in the experiment described here, you've got 89 grams of ethanoic acid, which is this thing here, which I've highlighted in black. And it gave 49.2 grams of aminoethanoic acid, which is shown here in green. And it also tells you that the MR is 75. Calculate the percentage yield of aminoethanoic acid. Give your answer to an appropriate number of significant figures. Well, looking at all the data here, I think 3 significant figures is going to be the way forward. So we start off by working out the moles of ethanoic acid. So you've got 89 grams, which you divide by 60. That'll give you the moles of the ethanoic acid. You then times that by 75, which will give you the what we call the theoretical mass of the aminoethanoic acid, the maximum amount that you could make. So 89 divided by 60 times by 75, and that gives me a theoretical mass of 111.25 grams. But it then tells you in the question that they only had 49.2. So it'd be 49.2 divided by the 111.25 times by 100. And the 3 significant figures, that comes out as 44.2%. Right, the next question is about the reaction of propanal, which is an aldehyde functional group, with hydrogen cyanide via nucleophilic addition, and it asks you to complete the curly arrow mechanism for the reaction using curly arrows and charges as appropriate. So the first thing to notice is that the carbon of the C triple bond N should have a negative charge on it, a full negative charge. So we put a minus in a circle there. Second thing to notice is the carbon double bond to oxygen is polar. So you need to have delta plus and delta minus there. So let's draw the first set of curly arrows. The C triple bond N is negative on the carbon, and this negative carbon is attracted to the delta positive carbon here. So we have a curly arrow going from the carbon to the carbon, which shows that a new bond is being made between these two carbon atoms. And then the second thing that happens is that this double bond, the electrons in the double bond, move from the double bond onto the oxygen. So you have a curly arrow going from there onto the oxygen. So what that means is that we've now formed a new carbon to carbon bond. So we should have a straight line going between the two carbon atoms. This double bond between the carbon and the oxygen has now become a single bond, but the oxygen has now become negatively charged. So it should have a negative charge on the oxygen. And then you've got a hydrogen that comes along here, which is positively charged. So you need to put a positive charge on the hydrogen. And then we have a curly arrow going from the negative oxygen to the hydrogen, which shows then the formation of our product. And that's the nucleophilic addition reaction, where we're adding hydrogen cyanide across the double bond. Question 8 is about ethanoic acid being heated with urea. And it tells you that when you treat a carboxylic acid with urea, you form an amide, carbon dioxide and ammonia, and you're asked to give an equation for the reaction. So ethanoic acid is CH3COOH. Urea is NH2CONH2. And the products are ethanamide, which is CH3CONH2. Carbon dioxide, CO2, and ammonia, which is NH3. If you're trying to visualize what ethanamide looks like, ethan means two carbons, and amide then would be a C double bond O to NH2, and a single bond to NH2 even, and then you've got a CH3 group here. So that's your equation, and suggest why an amide can act as a base. The key thing that they're looking for is that the nitrogen atom in the amide has a lone pair of electrons. Which means it can accept H+ ions. So it's an H+ or a proton acceptor. But you have to be very specific there and say it's the nitrogen atom that has the lone pair of electrons. So this question is also about nucleophilic addition, because you've got benzaldehyde reacting with hydrogen cyanide, and you're asked to complete the equation below. So you would still have a benzene ring bonded to a carbon, but then what happens is this carbon here is now bonded to the nitrile group, CN. It's bonded to the original hydrogen, but then the hydrogen of the HCN bonds to the oxygen to form an OH group, like that. And give the formula of the nucleophile that takes part in part A. It's based on the hydrogen cyanide. It's not simply acceptable to say that though, because the actual nucleophile must be negatively charged. So you've got your C triple bond N from the cyanide with a negative charge on the carbon, and that would be your nucleophile. Okay, so in this experiment here, this question, you've got amide T reacting with sodium hydroxide to form the salt of the carboxylic acid and ammonia. And you're told that in an experiment you've got 3.90 grams of the amide, and it produces 0.06 moles of ammonia. In terms of the stoichiometric ratio, 1 mole of amide T produces 2 moles of ammonia. So therefore the moles of the amide must be half that of the ammonia. So you end up with 0.03 moles of the amide. So if we know the moles and we know the mass, we can work out the molecular mass. The molecular mass is equal to the mass divided by the moles. So that's 3.9 divided by 0.03. And that comes out as 130. Now you get one of the 2 marks for that, but we now need to work out what this R group is here. So to do that, we need to know the molecular mass of this section of the molecule here, which is 44. This section over here must be also 44, which is 88 in total. So 130 minus the 88 gives you 42, and that corresponds to C3H6. So that's what our R group must be. It must be a propyl group in the middle, C3H6. Okay, so this question here is all about an organic synthesis. You are starting with this molecule here. This molecule here contains an alcohol group and a alkene. In the first stage, you're turning the alkene into a halogenoalkane. It's a reaction with HBr and its electrophilic addition. And then you're substituting the bromine for an OH, that's nucleophilic substitution in stage 2, and then stage 3 you're oxidizing the alcohols to ketone groups. But anyway, it says give the molecular formula of oct-1-ol. Very difficult to say. So firstly, I'm going to get my highlighter pen and work out the number of carbons. So 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be C8. Now we need to go back and count the number of hydrogens. So you've got 3 here, 2 here, 2 here, 2 here, 2 here, 1 there, but also 1 there, 1 there, and 2 there. So that's 16 in total. And then you've got 1 oxygen, so it'd be C8H16O. State a reagent that can be used for stage 2. So stage 2, you're going from the bromine to the alcohol group. That's the nucleophilic substitution reaction. And to do that, you need to reflux it with aqueous sodium hydroxide. Now reflux is not a reagent, so we don't need to say it, but it would be NaOH aqueous or aqueous sodium hydroxide. And state a reagent that can be used for stage 3, so it's the alcohol oxidation, so you'd need to say acidified, that's really important, acidified potassium dichromate. And it's very important if you write the name that you give the oxidation number of the chromium, which is 6, so 6 in Roman numerals. It then says an isomer of the oct-1-threol was reacted with alkaline iodine and produced a yellow precipitate. This is the test for the methyl ketones, and the formula of the yellow precipitate would be CHI3. And suggest a structural formula for this isomer and suggest the group that enables it to produce this yellow precipitate. So it needs to have a methyl ketone. We know there's 8 carbons, so 1, 2, 3, 4, 5, 6, 7, 8. If we put the ketone group here, then this would give us C8H, 3, 5, 7, 9, 11, 13, 18, 16, sorry. O, and the group that's responsible for the yellow precipitate is a methyl ketone. So that is a CH3CO. it then says octane 2,3-dione, which is this molecule here, is a pale yellow liquid, and octane 2,3-diol is a colourless material. State a reagent that can be used to produce the diol from the dione. So this is to go backwards, in other words, to do the reverse of this reaction. So to go from a ketone to an alcohol, you'd use sodium borohydride, NaBH4. You could use lithium aluminium hydride, LiAlH4. And suggest how the rate of the reaction could be studied. Well, bear in mind you're going from a yellow liquid to a colourless material, so you'd use a colorimeter to measure changes in absorbance. And we're almost done. We've got chlorobenzene here being nitrated and then made into this amine here, 2,4-DNPH, which is an important chemical test for aldehydes and ketones. But it wants to know about the mechanism for the nitration. So here you've got chlorobenzene reacting with the NO2 plus ion. So what happens is the pi cloud in the benzene ring is very electron rich, and it's attracted to the NO2 plus ion. So that gives you a curly arrow going from the center of the pi cloud to the NO2 plus. You then have to draw the intermediate. So you draw out a hexagon, which is your benzene ring, a positive charge because you've used some of the electrons from the pi cloud, and this positive charge is delocalized across the whole ring. You've still got your carbon to chlorine bond. We're now forming a new bond to NO2. And then we show the carbon to hydrogen bond. Now that was there already, but it becomes important in this stage because this carbon to hydrogen bond breaks, pushing the electrons back into the ring, reforming the pi cloud, which gives you your nitrated product. And this mechanism is called electrophilic substitution. So the NO2 plus is acting as an electrophile, and it's substituting for a hydrogen on the benzene ring. So electrophilic substitution. And state the feature of 2,4-DNPH that enables it to react as a base. It's the lone pair of electrons on the nitrogen, on the NH2 group. So it's the lone pair of electrons on the nitrogen. Anyway, that was a lot of questions, but thank you for taking the time to watch it, assuming you've got this far. You've done very well if you have. I hope it was helpful. I hope it will help you get ready for your organic chemistry exam. And if you found the video helpful, remember to like, subscribe, share with your friends. Keep checking back for more content. Thanks everyone. See you next time.